Today I'm talking to the CSRA interest group of Society of Decision Professionals, SDP. This will be the final presentation of this series of meetings where we've been discussing CSRAs, starting from how you start to frame the problem, assessing the uncertainties, how you utilize the modeling techniques, and reporting out. Society of Decision Professionals is supported by a number of organizations, as you can see here. So the presentation outline today is want to review how we frame the evaluation. We want to talk about the key schedule uncertainties in the initial evaluation, clarification of what's included in some of the activities. We want to schedule uncertainties with CDFs with a comparison to the baseline. Key cost uncertainties. After assessing the schedule uncertainty, we want to assess the cost uncertainties in the initial evaluation. Then we have a comparison of the cost uncertainties with the baseline cost, as we did with the baseline schedule. And typically, we're going to find that those are not very close. We'll talk about the critical path graphic, which I think is really important. We'll see why as we go through some of the other charts. There's a joint confidence level chart, and we're going to use 50% on that. And then we'll talk about the mitigations, where we actually make some decisions. And then we want to look at the final cumulative distribution chart and compare that to the original assessment. And then there's the process of, well, eventually we have to set a budget for this project using the final JCL chart. So any CSRA really should start with the frame. And then we're going to use the example of building a house. And it's going to start with signing of a contract to build this house. And at the end, the CSRA is going to end when the house is sheltered. In other words, we're not going to put in all the electricity and everything inside and do a paneling of the walls. We just want to get the roof on, basically. In the CSRA, we need to assess 18 different schedule tasks. We're going to estimate both materials, that's the dollars per task, and then the labor cost, the dollars per day, depending upon how long the task lasts for each of the tasks. An area of controversy are the estimates that you get from the subject matter experts. This particular example, we're going to use a P10 5090, although my preference would be use a minimum, most likely a MAC. But we're going to use P10 5090. A PERT diagram is very useful in explaining to the decision makers what was actually assessed and what were the tasks. So this has been laid out, starting from the left here of getting the contractor contract, through the framing of the house, coming down here and getting the windows installed, and the skylights, and then finally we have sheltered the house, and that's where it ends. In this particular model, there are 18 tasks that are all finished to start. However, generally there's going to be some times when it may be finish to finish, or start to start, or the leads and lags. So there's lots of different options, but in this case it's pretty simple. They're all finished to start connectors. Now another chart that's useful is the Gantt chart with the baseline estimates. So this was the P50 input from the subject matter experts. This represented the baseline time in order to complete the house. And as we can see, it's 158 days. So 158 days is right there, okay? We can see that some of these tasks are longer than others. Some do start at the same time. They're all tied into this framing as an example. But after we've done the CSRA, at least using the initial data, we find out that the mean completion time is 196, 38 days longer. Now this is just one simulation, not necessarily with the mean. It's an example of 196 days, 196 days. Now it's important to understand what is contributing to the schedule. So one way to do that is to look at the sensitivity of the minimum and the maximum, or in this case the P10 and the P90 values. And so here's the 196 days right through here, 196. And if I took the design and went to the P10, everything else being uncertain, because this is an EV tornado chart, you can see there's a significant move in the time to complete the house. Or if it went to the P90, there's a significant increase. That's also true for the window order and the framing. Now the following 6 tasks here also have some impact. Also notice most of them are very symmetrical. And that's because of the way the assessments were made with the P10, 50, and 90. Typically, they're not quite that symmetrical. So here are the cumulative distribution functions for the elapsed time. So here I've shown it 2 different ways. Here's the baseline cost, baseline schedule of 158 days, and here's the probabilistic one. So the schedule comes out around the, well, let's say it's saying the P15 here. The EV schedule is 196, so here's the EV, 196. But it could take as long as 300 days way out here on this tail end. And then this graphic is the same, except I've converted these days for the schedule into dates. So depending upon what the decision maker wants to think about. We can do something similar for the cost. We have a tornado chart, an EV tornado chart. And I will note that both material and the labor move together. So when the material is low, so is the labor cost, or vice versa, a high. The mean cost is 403 versus the baseline of 365. Here's the 403 down here in this EV tornado. And here we have the cumulative distribution functions for the cost. And we'll see here that the baseline actually here is more like a, what is it, P30 it's showing. Now this particular model, because of the way the variable costs were calculated, we calculated the total variable cost and then the material cost. The material cost being basically this green line, which is pretty vertical. In other words, not a lot of uncertainty in the material cost. But when you get to the labor cost, there's quite a bit of uncertainty, because you have uncertainty in the labor cost itself, a P10, 50, 90, and then you've got the uncertainty in the schedule, and those things get to multiply together. So you take 2 variables, multiply them together, what do you get? Something that looks kind of log normalish rather than normal, and that's what you're kind of seeing here. So another way of thinking about this is what tasks deserve the management attention. And what we can do is plot a graph here of the range of the input days. So what's the difference between the P10 and the P90? And here's the sensitivity to the EV days. So things that are on this line, this is a 1-to-1 line. So this is going up to 45 and 45. Since the design has a 40-day differential, and it changes the EV by 40 days, it's always going to be on the critical path. Any change in design will be 1-to-1 on the EV schedule. However, there's some that have very little impact. We can see that lighting, skylight install, and the sheathing have little impact on the EV. So this is another way of looking at the sensitivity. Now another way of looking at the model is through the critical path. It's going to tell us something different. So what we see here is the first 5 tasks are always critical. And that's because they're some of the first elements in our PERT diagram. And they always have to go through there. Now framing, let me go back to the framing here, you can see everything has to go through framing. So if framing takes longer, the whole EV schedule is going to change. The next 4 tasks are on the critical path 80% of the time. So here, or 86%. I guess these are 80 to 86% of the time. And management needs to focus on those tasks as well. But being on the critical path may not afford an opportunity to improve the schedule. Now let's combine the tornado chart and the critical path together. So on the x-axis, we'll put the criticality. That's coming from the critical path diagram that we just showed. And over here is the severity of the change in each of the tasks. So what we're really looking for is things that are up in here, up in this top quadrant. Those are the ones we want management to focus on. So this is going to be the framing and the window order and the design. Those are the things where we can have the biggest impact on our project. Now these down here are critical, but we can't probably do too much with those, the subject matter expert estimates. But what we can do is change the relationship of the activities. So in other words, can we change the relationship of the activities such that perhaps things can start concurrently, or they can start earlier, or something of that nature. And that could improve the schedule. Take them off the critical path. Remember, we're trying to move them to the left here. We don't want them on the critical path. So we can look at mitigation alternatives for these as well. The signing contract and the sheathing are not shown because they have no impact on the EV schedule. What does that mean? They're never on the critical path. Let's look at that. Signing contract and sheathing are not here because they're down here at 0. I've taken those zeros out. So typically the U.S. government wants a 70% confidence level of being under budget and being on schedule or better. However, let us look at only 50%. So what we want to do is find some combination that puts 50% in this quadrant over here. So now that we understand what our base schedule is and base costs, what can we do to improve it? We want to mitigate it. So one thing we could do is we could expedite the window order. It was high on the sensitivity. But labor costs could be more if we expedite the windows, and there's only a 50% chance of being successful. One of the traps of the CSRA with mitigation is to assume that every mitigation is 100% successful. So this model is set up where you can assign a probability to the mitigation working or not. So another mitigation is do some of the framing off-site and then bring it to the construction site. This reduces the time for the framing, but there's some additional cost due to the transportation of those framing parts and bringing them to the house. And there's probably only a 75% chance of actually being successful. And then we talked about these critical path, and what we want to do is change the precedence of activities to try to improve the schedule. So we could order the windows 30 days prior to the framing being completed. So there's an implicit assumption here that I know when the framing is going to be done, I guess. But let's assume we can figure that out. And we can order the windows 30 days ahead of time. Or in the base case, we're ordering them after the framing was done, and we can actually go in there and measure the window openings. But there's no associated cost with this decision. And let's assume there's a 100% chance of being successful because it is a decision. So what are the impact of all these mitigations? Well, on the time, it takes our reference days of 195.96 and reduces it to 172. You can see how the S-curve moved to the left here. Here's our baseline. Before we were here, what we said this was 15%, and now it looks like we're closer to 35%. And on the cost side, it actually increased it because we did things that were going to cost money for the mitigation. And so the EV cost increased from 403 to 423. We had a base cost here of 265. So we're even getting further away from our base cost. We can then look at our critical path with all the mitigations. And framing remains on the critical path, even with the mitigations in place. This is just a pinch point in the PERT diagram. So unless we change that pinch point, it's always going to be on the critical path. These activities are all 79%. Remember, they were 80 and 86% before. Window order and window install, which we worked on, we mitigated those, are now less likely to be on the critical path. So we can see the impact of our mitigations. And we now have an opportunity to mitigate the skylight order and the install of the skylights. So that might be another mitigation we could look at. We can also look at the impact of each of these mitigations separately rather than collectively. So if we rush the window order, schedule impact is 3.7 days earlier at a cost of 4.8. Framing off-site saves us 5.5 and the cost is 15,000. Ordering the windows 30 days prior to finishing the framing saves 16 days and doesn't cost us anything. And if we did all three of these things, we get 23 days, 24 days at a cost of $20,000. So then what do you want to do here? What would you like to do? Would you do them all? One way to think about it is to order them by their capital efficiencies. So I've ordered these and then plotted them in a kind of a pseudo efficient frontier. So over here we can see the window being ordered 30 days in advance. The next bullet is pre-ordering the windows relative to framing. And the third is changing the framing. Well, I'm going to assume we're just going to mitigate by ordering the windows. So we can look at those CDFs. And we can see here that the reference schedule of 196 days moves down to 179 days. And there is no change in the cost because we could say there was a no cost to that particular mitigation. So then we can look at the updated JCL chart to have a 50% probability of achieving both the schedule and the cost. The scheduled day, if we have scheduled days of 188 days, which is really the P65, so this is going to be the 188, and a cost of 412, which is the P65. Here's 412. We then get our 50% down here in this quadrant. So to summarize, there's a number of different charts we can use to explain what is this current situation with the CSRA. We have the PERT diagram, we have a Gantt chart, we have this EV tornado chart that tells the sensitivity of the tasks or the costs. We have the JCL chart that if we want to look at the probability of meaning both the cost and a schedule, what are the budget and the schedule we should be assuming. Those are not going to be the P50 if we want a 50% chance. And then we have the critical path diagram that tells us how often things are on the critical path, which then suggests that we should look at different ways of doing the task to improve the schedule. And finally, we have our CDFs where we can compare the reference schedule to the mitigated schedule. If you're interested in learning more about SIPMath, you can go to www.probabilitymanagement.org and you can download the SIPMath toolbar over here at Tools. You can download either the PC version or the Mac version. Thank you for watching. If you'd like a copy of the model please contact me at brian@theputz.com.